All right, I'm back. Wow. Um, Technology. It makes our life better. Well, okay, so let's start over. So, 20 minutes late. 15 minutes later, let's recap what I was talking about earlier. So, welcome to Monday. Hope you had a great weekend. There's two problem sets posted for you on WebAssign to work on simultaneously. They're not due on the same day. They're staggered. One's due a week from today. One's due a little bit later. One is called Work in uh, Energy and deals mainly with work in the concept of kinetic energy. The other is called Potential Energy, but they're related. And so as we continue talking about work and energy today, what I want to do is um, introduce derive the work energy theorem from beginning to end, and sort of go through the whole theoretical structure of this unit on work and energy, and then we can do specific examples, more specific example type problems. Okay, so they're posted at the same time because they're related to one another, and you can read through both assignments and sort of pick and choose which problems you want to do when. Just keep an eye on the due dates. All right. The other big thing that I announced when we had our before we had our problems this morning was that I'm going to move the next exam from a week from it's scheduled on the syllabus for a week from this Friday, and I'm moving it to the following Monday. So your next exam, exam 2, will be 2 weeks from today. That is what date is that? October 19th. Monday, October 19th is your next exam, and it'll cover Newton's laws of motion and work and energy. Okay, so the stuff we just finished and the stuff we're talking about now. All right. So mark your calendars. I'll remind you again. There's only 9 of you in here right now. I'll try to remind you every day between now and next week. Okay, so let's go to the whiteboard, and I got it working now. Yay! And recap what we were talking about last week. Also, the recitation on Friday, last Friday, was not well attended, and we might need to reconsider what's happening on Fridays. I want to make really good use of that time, and I thought we did make really good use of that time. But are you making really good use of that time? So the students who come to the recitation, if you need it, you should definitely use that time, because I think the students who are going to come to that session are just going to do so much better on the exams, so much better on the homework, and just it's a high impact time because we're face to face, and so the dialogue we can have, the back and forth we can have, is just so much better than remote. All right, so we're limited, but we do have that opportunity. You should take advantage of it if you can. All right, so recap. Last time we were talking about I introduced a new concept called work. And initially we defined it as work. Now, here's W again. It's not weight, it's work here. So from now on, I think when I write down the force of gravity, I'll use the F sub G instead of a W so we don't get confused. I said that work is a dot product between a force and a displacement. And what's the dot product mean? It means that if you have two vectors, F and delta x, a displacement, the dot product is the product of the magnitudes and the cosine of the angle between them. And what that effectively is you imagine, let's move this down here, that you take F and you project it down onto the displacement vector, and a portion of it is parallel to delta x, and it's only that portion that matters when it comes to work. It's the portion of the force that's parallel to the displacement. So work is then a scalar quantity. It's the magnitudes of these two vectors times the cosine of the angle between them. All right. So we're gonna rewrite this expression for work a little bit later to take into account, well, what happens if you're not always moving in a straight line, or the force changes as you go from point A to point B. And some examples where that might happen is the lab for last week, Hooke's law, where the force is position dependent. It depends on x. So if you don't have a constant force over the total displacement, you got to do something different than just multiply magnitudes. All right, we got 17 in here now. That's good. All right, so you guys joining us late because I had technical problems. The most important announcement I made at the beginning of class was the exam is 2 weeks from today. It's supposed to be a week from Friday. I moved it one day in the future to Monday, October 19th. All right, that's when our next exam is, exam 2. All right, back to the whiteboard. So in the realm of work and energy, there are forces that are referred to as conservative forces. And conservative forces, that word conservative means that something isn't changing. Something is remaining the same, okay, or is to say it's conserved. And when you look up, so this is like one of those situations, just like when we started talking about work, and I said, you look in your textbook for a definition of work, it'll say something like, work is a force over a distance. Work is a force applied over a distance. And as we're developing the concept of work, I said, the way I think about work is a measurement that we can calculate. It's a number that we can calculate to reflect a phenomenon in the real world where energy is changing forms from one form to another, or it's moving from one object to one or more other objects. So it's moving from one place to another. And there's still, even with that way of thinking, there's still like these nebulous concepts of, well, what is energy? It's not really something that you observe unless it's changing forms. If you think about that, if I have a gas tank and it's just sitting next to my lawnmower in the garage, there's a lot of energy there, a lot of stored energy. But you don't really observe that energy until I put it into my lawnmower and drive around my lawn cutting the grass, and then you can see that energy changing forms and being used to do something useful. So conservative forces is another one of these sort of nebulous concepts. I can say, if you look in your textbook, you'll see definitions like this. A conservative force is a force that does work, or I should say, when conservative forces do work in the physical sense, the amount maybe I'll write this a little bit more carefully. Oh no! All right, now I got to start all over. Conservative forces, I'll write it a little bit more carefully. When these do work, the amount of work doesn't depend on path, or I'll just say is independent and so work is the idea of path is sort of is embedded in the concept of work. A work is a force that's exerted over a distance, or a force over, multiplied by a displacement. Then there's a path that involves that concept of work. You're going along some path, and that path could be a straight line, it could be a sequence of straight lines that change direction, or it could be a curvy path. And so one of the characteristics of these things called conservative forces are when these do work, the amount of work is independent of path. So, one way I could draw that is it's like, if I have a starting point A and an ending point B, and there's some force acting in the vicinity here, and I go straight from A to B, so that's a path. Here's another path. Here's another path. So the idea of a conservative force is if a conservative force is acting on that object as it travels, all of those paths would give rise to the same total amount of work. So a related concept, I guess you could call it a corollary of that, is if you start at a point and let's use red. You start at a point here and you follow a path that takes you back to where you started. If you have a conservative force acting on that path, the work done by that is called W sub C is equal to 0. If you start and end at the same spot, the total work done by conservative forces would be 0. Okay, so those are like the textbook definitions of what makes a conservative force. But let's develop this a little bit more using mathematics, and then hopefully arrive at a more natural conceptual understanding of what a conservative force is. If there's conservative forces, there must be non-conservative forces, and if we discover what some conservative forces are, everything else that's not in that category must be non-conservative forces. And so we if we let's develop one of these. Let me tell you what one conservative force is, and there's two that you know about right now. Gravity. The force of gravity is a conservative force. The other one that you know about is the elastic force, as described by Hooke's law. And so these are conservative forces. So let's take a look at a situation where you have a ball that gets pushed up a hill, and obviously there's a pushing force, there might be friction, there's all these forces, but all we're going to do is focus on what gravity does, the work done by gravity, as this ball, whatever, gets rolled up a hill, and then it falls down, falls off the top of the hill. All right. And all right. So what I'm talking about is a situation like this. You have a hill, and there's a ball of, let's draw it a little bigger. It's a ball, and it gets pushed up the hill, and then when it gets to the top, it falls back down. Okay, so we can call this point A, point B, and point C. And let's ask, what is the work done by gravity, so I'll call that W sub G, when the ball moves from point A to point B? And so in order to answer this question, we've got to come back over here and look at our definition of work a little bit differently. If work is this dot product between force and displacement. Well, in this case, we don't have displacement in a straight line. We have displacement at a diagonal. Well, it is a straight line, but it's not one-dimensional. So another way you can write work is it's the force dotted into, let's call it a delta R, where delta R is a displacement vector that has an x component, a y component, and a z component. So I can write out that vector like that. There's a delta x, a delta y, and a delta z. I hat, j hat, k hat. And we could also say that instead of thinking about the total path from start to finish, we can think about moving along a path one little tiny infinitesimal piece at a time. So instead of a delta r, we can think about a dr. All right, calculus, inbound. So this little infinitesimal displacement would have an x component, a y component, and a z component. I hat, j hat, k hat. And then we can say for every little tiny piece of trip along this path, the amount of work is an infinitesimally small amount, dw, equals f dr. Okay, so we have and so this is a more general way of thinking about work in situations where you're following a curvy path or a path that changes direction. But the other application is, well, what if the force isn't constant? The force changes at every point along your path. And that's not true of gravity, at least gravity near the Earth's surface, because we're gonna model gravity near the Earth's surface. It's just the mass of an object times g. All right, but for the case of the spring force, Hooke's law, this elastic force, that's true because the force depends on stretch. So if you're stretching a spring, at every point along that stretch, the force is different. All right, so we'll take a closer look at that in a future day, at a future point. But do you see where I'm going now? Let's go over here. Keep all that on the screen. So if the infinitesimal amount of work done over this infinitesimal small displacement dr is f dot dr, then the way you figure out the total work along the whole path is by integrating. So the work done over the whole path is the integral over the path of f dot dr. Okay? So we'll keep this in mind. As we go forward. Okay. So now back to this question of this little ball rolling up a hill and then falling. And so let's take a look at the work done by gravity as the ball goes from point A to point B. Well, as the ball's moving along, you know, at any point, we'll draw a little spot here, at any point, the ball is being acted on by gravity. And the force of gravity, always points down. And, you know, the ball starts from where it starts, it has an initial x position and an initial y position called 0, and it rolls until it gets up here. We can give like actual numbers here. Let's say x final is 3 meters and y final is 2 meters. Okay, so we can think about the work done by this force of gravity as it goes from point A to B as the integral from point A to B of the force of gravity dotted into dr. And so the way we can write that is, well, dr is this composite of, there's an x part, a y part, a z part, and here we can ignore the z part because there is no z part, but there is a, there is an x and the y part to the situation. And so we can write that's equal to the integral from x naught to x, so in the x direction, of the force of gravity in the x direction dotted into dx, plus the integral from y naught to y, so the change in y, the force of gravity in the y times dy. And so if you think about this, well, the force of gravity doesn't point in the x direction. It doesn't point in the x direction. It only points in the y direction, the negative y direction. So this term is 0. So this whole term, this whole part is 0, it goes away. And the work done by gravity as you go from point A to point B is just the integral from y naught to y okay, and I should put the little vector notation in here. And so now let's think about this dot product. Okay, so if we think about, let's go over here, the dot product. If we think about going from point A to point B, our displacement in the y direction is up. We're moving up. And the force of gravity is pointing down. So the angle between those two vectors is 180 degrees. And the dot product is the cosine of that angle. So the cosine of 180 degrees equals -1. Okay? So what we have over here is, let's write in the force of gravity. It's mass times g times dy, cosine of 180 degrees. The dot product is the cosine of 180 degrees. So that brings a -1. M times g is constant. We can pull that out in front. So we have, and the cosine of 180 is -1. So we have the integral from y naught to y of these little infinitesimal changes in y. What is that? Well, we could be a little bit more explicit here. But if you integrate from some initial position to some final position along one dimension, the total is just the total displacement. So here we go. We got a result. Circle it in green, and I'll write it again up. I'll write it down here. The work done by gravity when you go from point A to point B equals negative mg delta y. The work done by gravity is the negative of the weight of the object times its change in vertical height. That's what this is saying. The work done by gravity is the negative of the weight of the object times its change in vertical height. Final minus initial. So here, the work done is a negative quantity. All right, that's interesting. All right, now let's look at the work done by gravity when you go from B to C. Okay, so you're falling straight down. And so that would equal the integral from B to C of the force of gravity dotted into the displacement. And so we could write out there's a potentially an x component, a y component, and a z component, but it's straight down, so we can ignore the x component and the z component. This is going to be the integral from y to y naught of the force of gravity dotted into dr. The y, dy, sorry. So there's only a y component here, dy. And so let's look at this again. So if we have, now if the ball is falling, its displacement vector points straight down, and so does the force vector, the force of gravity, points straight down. So here you have an angle between these two vectors of 0 degrees. So when you process the dot product, cosine of 0 degrees is 1. So this becomes the integral from y to y naught. You're falling, so from the top to the bottom. The force of gravity is m times g dy, and the cosine of 0 is 1, so it just goes away. Again, the mg is constant, so you have the integral from y to y naught of dy. And what is that? That's just the displacement again. So when you go from the work done by gravity, when you go from B to C, is equal to mg times the change in y. And so we'll circle that. And we'll look at these two expressions. All right. So you have here, let me come over to the webcam here. So you might be thinking, well, if you're going in the opposite direction, wouldn't the delta y be negative here? But the dot product sort of destroys that, because the dot product involves the magnitude of the vectors. It's just the magnitude of the vectors times the cosine of the angle between them. So if I was being more careful, that I would have used like the vertical bars to show magnitude. The final result that we get here is, well, we're not back to where we started, but we kind of are in one dimension, the dimension that matters. Let's zoom in here. So if I go from A to B, my delta y is 2 meters. And if I go from B to C, my delta y is 2 meters. Just magnitude, right? The dot product destroys the notion of direction. And so when it comes to y in the y direction, if we go up 2 meters and come back down 2 meters, we're back to where we started. If I go from C to A, back, left, from C back to A, gravity doesn't do any work at all, because the angle between that displacement vector and the force of gravity is 90 degrees. All right. So we have an interesting thing here. So we can see that the work going in one direction equals the negative work going in the other direction. And this is exactly one of those criteria for a conservative force. That if you go in a loop, you go one direction and then you come back and you go back to where you started, the total work done is 0. So you do negative work in one direction, positive work in the other direction. The total work done over the whole loop is equal to 0. And so we could figure out, other paths. If I, instead of going, up the ramp, I could say, what's the total work done by gravity if I first go horizontally and then up? I get exactly the same number. I'd break it into 2 paths and get exactly the same number. Okay, so what we have here is this quantity that we ended up calculating, the weight of the object times the change in height in vertical distance, is actually referred. It's actually a kind of energy, it's called potential energy, gravitational potential energy, and it's stored up in the object. It's potential energy is a thing that's a quantity that's a consequence of the position an object has. And let me write this out here. So this quantity right here called gravitational potential energy. All right, get a little, and we'll use the symbol U to represent potential energy. It's equal to mg times y. So what we're calculating up here are mg delta y's. Well, that's a change in potential energy. And so this is another characteristic of the fact that conservative forces do work that's path independent means that there's a number that you can calculate for each point along the path that is dependent on position along that path. And we call this number potential energy. And what we find, though, is when we do the calculations, in absolute terms, the number doesn't really have much meaning. What matters is how it changes when you go from one place to another. All right, so that's a theme that we'll revisit a couple times. This number right here, mgy, which is weight times position, vertical position. You can calculate it for any vertical position, but when I say it doesn't really mean much in absolute terms, the reason is because whatever your value is for this quantity right here, your vertical position depends on where you define 0 to be. So you would get different numbers for this quantity if you say 0 is sea level, or you could say 0 is the height of Byrd Science Center in Shepherdstown, West Virginia. You could define your 0 point vertically to be anything, and then that would change the values that you calculate from this quantity. But what wouldn't change is if you go from one point to another, the delta is going to be the same regardless of where you say y equals 0 is located. All right. So let me put down one more thing before we call it a day. And so this is gravitational potential energy. So U is used to represent potential energy. And this is one kind of potential energy, gravitational potential energy, associated with the gravitational force. But one of the things that we discovered from doing all this work is the work done by gravity is equal to the negative change in gravitational potential energy. And so this is a standard result that you would get for any conservative force, that the work done by a conservative force is equal to the change in the potential energy associated, the negative change in potential energy associated with that conservative force. So if you have the gravitational force and you have an object and you're raising it up, gravity does negative work, which means that object's potential energy is increasing. Work equals negative delta U. So you're giving that thing potential energy, and if it falls back down, that potential energy is decreasing as it falls. So we'll look at the way that this new piece, the connection between the work done by conservative forces and potential energy, fits in with the piece that we learned last time, which was the total amount of work that's done on an object is equal to its change in kinetic energy. So we have these two types of energy now. One is potential, has to do with the position of an object, and the other is kinetic, which is the energy of motion. And we'll weave them together, we'll see how it all fits together, and we'll come up with one sort of, let's call it a master equation for work and energy called the work energy theorem, and then we can explore different specific cases, special cases within that realm. All right, that's it for today. So I'll see you guys tomorrow during the synchronous lab session. The lab this week is on the Atwood's machine, and then I'll see you on Wednesday, and we'll finish up the derivation of the work energy theorem and then start looking at specific cases.